So we're going to look at the next level of factoring. Before, when we were factoring, when we had our standard form, all of our values of A were 1, this value right here. What we're going to look at today is what happens when A is a number other than 1. And you'll notice I put a little note up here at the top. We have to always look for our greatest common factor before we do anything else. So I'm going to start with an example where we do have a greatest common factor. So our first example is 2x squared plus 14x plus 20. And you'll notice that all three numerical values here can be divided by 2. So what I'm going to do, and I'm going to do it this way just to show you what's happening. You do not have to do it this way every time. I'm going to divide each of these by 2 and then figure out what would be left over to multiply to get back to my original term. So 2 times what would give me 2x squared? Well, this is missing x squared. 2 times what gets me 14x? I would be missing 7x here. And then 2 times 10 would give me 20. So this 2 has been divided from each term. So that's going to go outside of my parentheses. And then what's left over is going to be x squared plus 7x plus 10. So because I factored out the 2 first, I now am looking at just this piece inside of the parentheses, that trinomial, and that's what we're going to factor now, which goes back to exactly how we factored in our last video since my A value is 1. So I'm taking 10 and I have to break down 10 into my factors of multiplication. So I have 10 times 1 and 5 times 2. So I'm multiplying to get 10 and adding to get 7. Well, that would give me 11, so that won't work. 5 times 2 does give me 7. So that's what's going to go. I'm going to go over here for a little bit more room. That's what's going to go into the box here. So x squared is my first corner. 10 is the opposite corner. Then I'll have 5x and 2x. Now I'm looking for common factors within each row and each column. So here, those two terms have x in common. These two terms have a 2 in common. In this column, my common factor is x, and in this column, my common factor is 5. So I've got x plus 2 and x plus 5. But this gets me back to x squared plus 7x plus 10, not to 2x squared plus 14x plus 20. And I need to make sure that I bring that 2 that I factored out into my final answer. So this is the complete factored form of this original quadratic. So that's what it looks like if you have a common factor. I'm going to move this down a little bit. The next one we're going to look at is 2x squared plus 5x plus 2. And I'm going to actually switch back over to the algebra tiles I used in the last video so that we can see what's happening. And I already have all of my blocks ready to go. So my 2x squareds have to be in the top corner. And if you think about how the box looked, the rectangle that we're setting up for every other problem we've done, the 2 singles or the constant goes in the opposite corner from the x squared. So now I'm going to try to start filling in the x's to see if I can make the 5x's fill into the rectangle this way, and I can't, I have this one left over. So what I'm going to do now, instead of stacking these singles side by side, because remember I'm trying to find the length and the width of this rectangle, I'm going to stack it that way. So now if you look at our box, I've got 2x squareds, 4x's, 1x, and 2. So I'm going to redraw that rectangle that we had on here. So I have 2x squareds in this corner. My constant went over here. I had 4x stacked underneath the 2x, and I had 1x in this corner. So now I'm going to look for my greatest common factors. I'm going to look at the length and the width on this case. So here, between 2x squared and 4x, they both have an x in common, but they also have 2. These don't have anything in common, so that factor will be a 1, or that common factor, excuse me. These have x in common, and this row has 2 in common. So my factors would be 2x plus 1 times x plus 2. Now, the question is, how do I figure out these two pieces without drawing the box every time, filling in with algebra tiles? Well, before, my coefficient was a 1. I didn't have to worry about anything other than taking this last number and breaking it down. But I can't break down 2 into factors that will add up to get 5. That doesn't work. Now that I have this coefficient in front of x squared, I actually have to take both of these numbers, my a value and my c value, and I have to multiply them together because the dimensions of this rectangle depend on both of these pieces, as you can see from the box that we already made. This side length here depends on the fact that I have 2 x squareds that I have to deal with. And this length down here depends on the fact that I have 2 single digits that I need to work with. So I'm actually doing 2 times 2, which is my a value times my c value, which gives me 4. And 4 is the number that I am breaking down into multiplication factors. So I could have 2 times 2 and 4 times 1. And now I'm breaking down the a times c to get this value of 5 for b. Well, 2 plus 2 would give me 4. That wouldn't work. 4 plus 1 gives me 5. That is where these two numbers came from. So we're going to do another one like that, but I'm not going to use the algebra tiles. We're going to actually do this just algebraically. So our example is, this is number 3. We have 3x squared plus 5x minus 2. So now I'm going to have to worry about negatives. So I'm going to start by taking my a value and my c value, and I'm going to multiply together 3 times negative 2, which means I'm breaking down negative 6 in my factors. So what two numbers multiply together to make negative 6? Well, I could have 3 times negative 2. I could have negative 3 times positive 2. I could have 6 times negative 1, and I can have negative 6 times positive 1. But my goal is to make 5. So the larger number in these can't be negative, because that would end up giving me a negative solution, or a negative number when I add together. 3 plus negative 2 gives me 1. That won't work either. Pardon me. 6 plus negative 1 gives me 5. So those are the corner boxes that we're going to use. So here is 3x squared. This would be negative 2. I've got 6x and I've got negative 1x. Now, of course, you don't have to put the negative 1 here. I'm doing this simply for the fact that this is our first example that's really working with negatives in this video. So these two have nothing else in common other than the fact that they're negative. So that'll get a negative 1. Going this direction, I've got 3x squared and 6x, so the greatest common factor in the coefficients is 3, and then they both have an x in common. Coming across this way, they'll both have x in common, and here they'll both have a 2 in common. Now I should, again, just as a double check, be able to multiply through and see that all of my boxes get filled in with the correct multiplication. So I'll have 3x minus 1 times x plus 2 as my factors. So now you've seen a greatest common factor example. You've seen 2 examples dealing with what happens when a is not 1. But there's 2 special cases that we're going to look at. Here's special case number 1. So this will be example 4. I have 4x squared plus 4x plus 1. All 3 of my values don't have a common factor. If this wasn't here, it would be a little bit different. And I'm going to show you that example in a minute as well, so you can see the difference in that factoring. But if I have a 1 here, can't do anything with factoring out of 4. So I have to go straight to the box. So this is going to be 4x squared, and this is going to be 1. So a times c, 4 times 1, gives me 4. So I have to break down multiplying by 4, multiplying to get 4, but then I also have to add to get 4. Well, there's only one way that that works, and that's if it's 2 times 2, which gives me 4. When I add, and 4 when we multiply. So this is going to be 2x, and this is going to be 2x. Well, 1 has nothing in common with either one of these 2x's, so those are both going to be a 1. 4x squared and 2x both have 2x in common. And you should notice at this point that both sides are exactly the same. That means I would write 2x plus 1 times 2x plus 1. However, if I have the exact same thing multiplied by itself, really I would write it as 2x plus 1 squared. So if for any reason, if you're given a multiplication problem that says something squared, that means really I'm multiplying the same thing by itself, which means I'm dealing with a perfect square where the sides are exactly the same. So just as a comparison, if I was given 4x squared plus 4x, and that's what I needed to factor, both of these can be divided by 4 and x. So what would be missing to get me back to 4x squared? Well, I'm missing an x. Here, I'm not missing anything, so I would multiply by 1. This is the common factor that's going to go out front. So I would have 4x times what's left over, x plus 1. So just to see the drastic difference if there is a common factor and if there's not a common factor. And I have one more for you. And this is one of those special cases that looks way more complicated at first than it really is. I'm going to show you this using the box method, but I don't expect you to ever use it after this with this type of example. Now you'll notice that there is no b value. So 9 times 4 gives me 36. So I'm multiplying to make 36, but adding to get 0. Oh, excuse me, it's negative 36. The only way that works is if I have 6 times negative 6. It's the only way I can multiply to get negative 36 and add to get 0. So I'm going to start filling out the box. 4x squared and 6x, they have 2x in common. Negative 6x and negative 9 have negative 3 in common. Here, again, 2x, but here they're not both negative, so that's just going to be 3. So I've got 2x plus 3 and 2x minus 3. And that would be my final factorization of 4x squared minus 9. But if you think about what types of numbers 4 and 9 are, I can get from 2 to 4 and from 3 to 9 by doing one operation. I could square 2 and get 4. I can square 3 and get 9. This only works if the a value and the c value are perfect squares. It's the only time it works, because I can break these down into their perfect squares. Now this also is going to have x's with both of these, and one of these 3's, since it's negative 9, will have to be negative. And you'll notice 2x plus 3, 2x minus 3. And again, this only works if there is no b value and a and c are perfect squares and there is a subtraction sign in between.